Okay, hi everybody. So I'm recording this from home. So if you hear crying, it's probably just my kids crying or one of my animals are crying. So bear with me. So we're going to talk about predicting products. And this is kind of like something that you guys already know how to do. But what we're going to be looking at is we're going to be looking at the types of reactions, but we're going to use what we know about the types of reactions and what they look like to predict the different products that we're going to have. So the first one would be combinations or synthesis. And in a combination or synthesis reaction, I don't know why there's a glare. In a combination or synthesis reaction, we know that there's two reactants that are going to combine to form one product. So we know that whatever two things we start with, we're going to create something at the end. The first thing that you want to do when you're trying to predict the product of something that's a combination reaction is you want to write the cation in ion form. So we have a metal and we have a nonmetal here. We have aluminum and oxygen. So we know that these two are going to combine to form one compound here. So what we need to do is we need to write the cation, and the cation for aluminum into our periodic table, which is here, is Al plus 3. And then we need to write our anion in ion form, which is O minus 2. So basically what you're going to do is you're going to take the two charges that you know comes from aluminum and oxygen, and you're going to put them together over here as the product. So if aluminum is plus 3 and oxygen is minus 2, what's my formula going to be for this compound? Well, I need two positive 3s and 3 negative 2s to cancel those charges out. So I'm going to have Al2O3. All right. Now, once you've predicted the products, well, now you have to balance. Well, you're just going to do your regular old atom inventory and then balance. And if I was to do that, I would get a ratio of 4 to 3 to 2. 4, 3, 2. That's what that would look like. Okay. Next one is same thing. You write the cation in ion form. The cation for sodium is Na, which is Na plus 1. And chlorine, the anion, is Cl minus 1. So if I know that this is a synthesis reaction, my two reactants are going to combine to form one product, well, I just have to put them together. So Na is plus 1, Cl is minus 1. So I'm going to get NaCl as my compound, which cancels out. And then once I figure out what my product is, now I have to balance. So when I do balance this, I'm going to end up with 2, 1, 2. Now I'm not doing the balancing examples because you guys already know how to do that. So I'm not going to waste time and sit here and balance. I'll just tell you what the ratio is. All right, now opposite of combination or synthesis is decomposition. So it's basically taking what we just did, but doing it backwards. So now you're going to be taking the one single compound and you're going to be breaking it down into simpler pieces. So first what you want to do is you want to write the metal and the nonmetal as products. So if we look at this compound here, we have silver and oxygen. So I'm going to write silver plus oxygen. Okay, here's my metal, here's my nonmetal, but can I leave the nonmetal oxygen as just an O? No, I can't, because if you remember, oxygen is a diatomic and oxygen can never be just one by itself. It always has to have a partner of some kind. So this becomes Ag plus O2. All right, now when I balance this, I'm going to find this isn't balanced. So my ratio for these is going to end up being 2 to 4 to 1 when I was to do my inventory and then balance. But I'm not, like I said, not going to do that, not going to waste time. All right, now this one is a little bit different. This one is a little bit tough. So we're going to actually scratch this one out and skip this one, because what's going to happen is magnesium carbonate is going to break up into more than just two products. And I don't expect you guys to know how to do that. And I'm never going to ask you to do that on a quiz or a test. So we'll just get rid of that one. But let's do an example that we already did. Let's say that we have Al2O3. Well, what I need to do, according to the directions over here, is write the metal and nonmetal as products. So my metal is aluminum. My nonmetal is oxygen. Well, I know oxygen can never be by itself, so what I have to do, add a 2. There you go. So notice that this reaction and this reaction are opposites of each other. All right, up next. So this is where things get a little more complicated, but not too complicated. So single replacement reactions are different. We're going to use something on the periodic table called the reactivity series to help us with these. So in order to predict a product for a single replacement reaction, we need to figure out what is happening. Who is going to be more reactive? So the way that we do that is we have to, in order for a single replacement reaction to occur, the metal that is trying to replace the cation has to be more active. So what that means is that we're going to use this reactivity series on our periodic table to help us figure that out. So if you look up here are the most reactive, and that includes lithium, potassium, right? And lithium, potassium are in group 1, and they're super reactive. Alkali metals are super reactive. Towards the bottom, we have things like copper, mercury, silver, platinum, gold, and these things are least reactive. We know that they're not very reactive because we make jewelry out of silver and gold. So jewelry, right, that people wear is made out of these metals because these metals are the least reactive. They're not very likely to react. Whereas jewelry is not made out of these metals because if you put lithium, potassium, or sodium in water, they're going to explode. So what you want to do is you want to take a look at the metals that are given. So we have sodium and we have iron. So if we take a look, here's sodium and here's iron. Now, sodium, according to this table, is more reactive. It's higher on the list, so it's more reactive. And iron is lower. So what you want to do is you want to look at, okay, who is with the anion? Here's my anion, here's my nonmetal. And right now, iron, which is less active, iron is less active, then sodium is with chlorine. So if the metal that's by itself, which right now is sodium, is higher on the reactivity series, that means that sodium can steal chlorine away from iron because sodium is more powerful or more reactive. So what's going to happen is this sodium, which is +1, and this chlorine, which is -1, which means that this iron is +2, the sodium and this chlorine are going to end up together, NaCl, and iron is going to end up being all by itself because sodium is going to be able to rip chlorine away because sodium is more powerful higher up on this reactivity series. So we would call sodium the top dog. They're more towards the top. They're the top dog. They're going to steal that ion away. Okay. Then if I was to valence this, which you're going to need to do, this would be a 2, this would be a 1, this would be a 2, this would be a 1. So we'd have 2, 1, 2, 1. And that's what that reaction would be. All right, next example. Let's take a look at this one. What I need you to do, I don't know why this example is here. This is supposed to be a sodium. I think whoever was typing it out just typed in S for sodium, even though sodium is Na. So let's take a look at Na and K. All right, so Na is right here, sodium. K is potassium. Who is more powerful? Who is higher up on the list? Well, potassium is higher on the list. So that means that if these two were to go into battle, potassium's going to win. Well, right now, potassium has the partner. So potassium is higher on this list, right? Potassium's up here. Potassium is winning. So if potassium is already winning, if potassium is already on top, that means that sodium does not have enough power, does not have enough reactivity to steal fluorine away from potassium. So if that is the case, right, potassium is more reactive and they're already with the anion, that means there's going to be no reaction that's going to happen. So you cannot balance this. You cannot predict a product because there is no reaction. So some of these reactions in single replacement you're going to find are not going to be possible. So if I'm asking you to predict the product for something that is single replacement, not only do you have to be able to identify what a single replacement looks like, but you also have to use this reactivity series only for single replacement. All right, up next, double replacement. Double replacement is a little bit easier. You do not have to use the reactivity series for this. Basically what you're doing is you're just taking the compounds, you're splitting them apart into their ions, and then you're rearranging them. So what I need to do first is I know this is double replacement. I know that my anions are going to switch partners with their metals. So what I'm going to do is I'm going to label what charges each of these ions have, and then I'm going to rearrange them. So calcium is in group 2, so it's +2. Sodium sulfur is in group 6, so that means sulfur is -2. Potassium is in group 1, so +1, and fluorine is in group 7, so it's -1. So in double replacement, I know that my metals and nonmetals are going to switch partners. So that means that fluorine is going to end up with calcium and sulfur is going to end up with potassium. So I'm going to end up with Ca plus 2 and F minus 1. So I'll get CaF2 plus K is going to end up with S. So that means I'm going to need 2 Ks, 1 S. So I'll have K2S. And then I'm going to need to balance. So if you were to do your inventory and balance, you would find that you'd have a 1, a 2, a 1, and a 1. So your final ratio would be 1, 2, 1, 1. Okay. Now, it doesn't matter which product you write first. I could have written K2 here and CaF2 here. It doesn't matter. What will matter is your ratio and the numbers that went here. So since these are both ones, this ratio doesn't matter. But if I was to switch these around, you have to make sure that your ratio matches the order of the reactants and the products that are written. All right, next one. We have sodium chloride and we have aluminum oxide. So again, pull the ions apart. So we know Na is in group 1, +1, chlorine is in group 7, -1. Aluminum is in group 3, +3. Oxygen is in group 6, -2. All right, so I know that they're going to switch partners. I know that oxygen is going to end up with sodium and chlorine is going to end up with aluminum. So let's write that out to reflect that. So Na is +1, O is -2, so I'm going to have Na2O plus aluminum is +3, Cl is -1, AlCO3. All right, so those are my products. Again, you could switch these around. They don't have to be in this order. This one could be first, this one could be second. But when you balance and you write out your ratio, which is going to end up being 6, 1, 3, 2, the order does matter. So this is 6, 1, 3, 2. So you need to make sure that the final ratio that you write reflects the order that things are in. All right, last but not least, the easiest ones to predict. We know that a combustion reaction is a hydrocarbon, some carbon-hydrogen compound plus oxygen will always create carbon dioxide and water. Well, if you can see that this is a hydrocarbon, a carbon-hydrogen compound plus oxygen, what is it always going to make? It's always going to make CO2 plus H2O, no matter what. This one, carbon-hydrogen compound plus oxygen, what is it going to make? It's going to make CO2 plus H2O, no matter what. Okay. If you were to balance this one is going to end up being 1, 5, 3, 4. And this one's going to end up being 2, 7, 4, 6. All right. So that's predicting products. That's how you do that. It's pretty easy. So I'm going to ask you to follow your calendars and only do the odds for the worksheets that are on your calendar for that day, or not the odds. So you're going to follow if you're in an odd class period, you're going to do the odds. If you're in an even class period, you're going to do the evens. All right, so some of the practice problems are going to be single replacement, some are going to be double replacement, some are going to be combustion, combination, decomposition. So you have to identify what they are, write their products, and then balance them. All right, bye guys.